Okay, so today we're going to begin talking about mass spectrometry. And one of the things about mass spec is that it has definitely evolved over the years. You can see we actually have a mass spec in our department. It was, I think we paid somewhere around $500,000 for it. And it looks some similar to this. It's a big instrument. It's a QTOF, so it's a time of flight instrument. But these are traditional mass spectrometers here. And then now we even have the capability to have portable mass spectrometers, right? So a portable mass spec, you've probably seen these in the airport where they swab your bag. And once they swab your bag, they take the little fabric and put it down into the instrument. That's a type of portable mass spectrometer. What they're looking for are chemical signatures from explosives and things like that. We started doing that sometime after 9/11, uh, testing for explosives in suitcases and on. Sometimes at the beginning of that, they used to even swab your hand and take a swab of your hand to see if you have had any type of residue on your hand. So even we're even to the point now where we have miniaturized mass spectrometers like the one you see here on the chip. Uh, very, very um, intricate technology. And then the thing about the miniaturized mass spec, I can remember as a postdoc at the University of Maryland, I went to a conference in Virginia, and this was the topic, right? How do we develop it? And we had this long workshop about developing miniaturized mass spec, and lo and behold, we actually have the capability now. Even I don't know how many of you. Well, you all should be old enough to remember when we first went to Iraq, and you see the soldiers walking around with these handheld devices. They were yellow, and what they were looking for actually looking for explosives and chemical weapons, right? So they would take the excuse me, take the handheld device, and they would pick up or try to pick up chemical signatures from the vapors in the air, trying to find out if chemical weapons were present. Right, so that was a big thing when the Iraq War first started, was the use of chemical weapons. So mass spec was kind of used to uh, facilitate that process. Right, so what do you use it for? You use it sometimes to identify unknown compounds, and that's when you compare an unknown to something that you know, you're able to kind of sift out uh, what the unknown is based on what you know. Right, you also use it to quantify known compounds, so compounds that you actually know and you have an idea of what you're looking for. A mass spec can help you to determine that. All right, you probably have all seen uh, like what's the show CSI and things like that, where they always have a scene where somebody from the show is in a lab with a lab coat on and they hunched over an instrument with a screen with some little graphs on it or something. More than likely, they're doing mass spec, right? Because there's a liquid chromatography version of mass spec that's also uh, available, right? So you use it to quantify known compounds. You use it to detect explosives. We already talked about that. Crime scene investigation and detection of contaminants or toxins in various samples. So you see, if you watch the video I sent, and you see how mass spec is actually set up. You have your sample, you inject it into an ionization source, and then from that, you that those fragments that get created. We're going to talk about that in a minute. You basically pound in this molecule like you beating it with a hammer, shattering it into pieces, and then the pieces get put into the mass analyzer, and then that mass analyzer detects the mass or atomic weight or molecular weight of every fragment that passes through it. And then that information comes to a detector. And then from the detector, that goes into a data analysis program where you can actually look at the spectrum and determine what you have. All right. So this is my rough estimate of, or my rough example of how Mass Spec works. So the lightning bolt is my electron beam, and so the electron beam is what's going to be that's your ionization source. That's what's going to pound on that molecule, right? So the electron beam is pounding on the molecule, and then after a certain period of time, that molecule is going to lose an electron, right? When it does, it becomes this structure over here, which is called a radical cation. And that radical cation then is fragmented further, right? So you lose an electron to make the radical cation, and then that gets fragmented, basically obliterated into fragments. And so here you have two fragments, right? You have your proton or a hydrogen, and then you have the CH3 fragment. And then one of those two fragments is going to become the cation, and one is going to become the radical, and that's based on stability, right? So you have the electron beam that bombards the sample. You have the ejection of an electron. You have the radical cation being formed and then being further ionized, not ionized, I'm sorry, further, I guess the best word I can find is pounded. So further pounded to shatter it and become fragments. And then those fragments get analyzed by your mass detector. All right, any questions so far? All right. So here's a mass spectrum, a sample mass spectrum, and there's some things in the mass spectrum that we can pick up immediately. The first thing is what we call the base peak. That's usually your tallest peak in the spectrum, and then you have your parent peak, which is going to correspond to whatever the molecular weight is of your compound. So if your compound has molecular weight of 50, the parent peak is going to be 50. There's some other peaks in here as well, what we call the M+1 peak, and that tells us it's just whatever the molecular weight is plus one. It's an isotope peak, right? So let's look at so we have the base peak label. It's the tallest peak, usually corresponds to the most stable fragment, and then you have the parent peak, which is at 45 in this case. And then the M+1 peak is at 46. All right. So here, let's look at another mass spectrum. So this says that you have 4 compounds to choose from, right? Formic acid, 1 propanol, ethanol, and methanol. Let me see if I can annotate this and draw these structures on here. All right. So you have formic acid, which is here. All right, and then you have propanol, and then ethanol, which is 2 carbons. And while I'm doing this, can someone look up the molecular weight for each one of these: formic acid, propanol, ethanol, and methanol? Methanol is 1 carbon. And then isopropanol.
No, 40.
All right, so formic acid, is it 46?
Yes, 4603.03.
So I'm gonna put that over here. Okay, thank you. Propanol, you said 60. I'm just gonna round them to 2 sig figs. Ethanol, I think, is also 46.
Yes.
Methanol is let's see, 1532. And then isopropanol, 60 as well. Is that right?
Yeah.
Okay. And this is all grams per mole now. Okay. So so we have 5 compounds, and let's rule out what can't be on the mass spectrum. Okay, so the mass spectrum is going to be at the maximum M plus 1. So whatever the molecular weight is plus 1, right? So at maximum. So what can we rule out immediately? Right? Which ones can we rule out immediately? Look at the spectrum. It's from 10 to 50, right? What can we rule out?
Isopropanol alcohol.
Isopropanol and 1
And
propanol,
mm-hmm.
right? Because these are 60 grams per mole, and the limit on the spectrum is at 50. So if a compound was in this spectrum that had a molecular weight of 60 grams per mole, then we should at least see a peak at 60, and then an M plus 1 peak at 61. And we don't see that. So we can rule those out. Is that clear to everybody? Is anybody not understanding that? All right, so we rule out 1 propanol, we rule out isopropanol. What else can we rule out? Can we rule out methanol? Methanol? Can we rule out methanol? Why or why not? If methanol was the main compound, where would the spectrum stop?
It will stop 532.
Yeah. And you see now you have peaks that are at 40, 45, 46, 47. So this cannot be the main compound that we're analyzing, methanol, because you have peaks out here at 45, 46, and 47. The spectrum for methanol should stop at 32, and then you'll have an M plus 1 peak at 33, and that's it. You wouldn't have anything else. Right? So our 2 choices are ethanol and formic acid. All right, so now we need to look. So the base peak is what? It's the tallest peak in the spectrum, which corresponds to which peak here?
31.
31. Good. And the parent peak, if it's formic acid or ethanol, because we're trying to rule one of these out, the parent peak would be what? If the molecular weight, if the mass spec is going to detect the molecular weight of the product or of the compound and any fragments, what is the parent peak? The parent peak is the compound or the molecule before it breaks apart. So what would the parent peak be?
45.
Think about it. Look at the molecular weight. The molecular weight is what? 46, is that right?
Yes.
So the parent peak is going to correspond to that. So the parent peak is 46.
Okay.
Are y'all following? So the base peak is 31. The parent peak is going to be 46. And then what is the M plus 1 peak?
47.
47, good. And then it asks here, what does the peak at 45 correspond to? What So if the parent is 46, the molecular weight is 46, what can I lose from that to give me a fragment that has a molecular weight of 45 grams per mole? What atom has a atomic mass of 1?
Hydrogen.
Hydrogen. Good. Okay, so this can be, so at 45, we'll put lost hydrogen. Are we following? Everybody okay so far? So
For N+1, you're just adding the parent peak plus 1.
Yes, that's all it is.
Okay.
Mm-hmm.
Dr. Russell,
Yes.
I'm still a little confused on the base peak. Can you explain that a little bit?
So
One more time.
it's a fragment, and it's the most stable fragment for this particular compound, whichever one it is. We're gonna figure that out in a minute. But the base peak is always going to be your most stable fragment. So if you look at the spectrum, the x-axis is mass over charge, and your charge is usually +1, so it's really just the mass. But the y-axis is relative abundance, right? And that corresponds to the relative abundance corresponds to the amount of a particular fragment that's present.
Okay.
So your base peak is going to be a fragment, the fragment that's present in the highest amount.
I got it.
All right. So now let's look at these two compounds. We got formic acid and ethanol. And we got to think about how we can break those apart to get these fragments. So let's start with formic acid. So formic acid, if I broke it, let's see if I can get this right. If I broke it here, are you following?
Mm-hmm.
What would I have? What two pieces would that give me? It would give me an H, right?
Mm-hmm.
And then it'll give me the carbonyl, the acid part, OH. And I apologize for that being sloppy, but I'm drawing with my mouse, right? So the H is 1, and then this other piece would have to be 45. Are you following? Because what I'm doing is I'm taking the molecule and I'm ripping it apart by bombarding it with the electron beam.
Mm-hmm.
Okay? So here's the question. What happens if I split it on this side? And we're going to talk about the fragmentation patterns too. What happens if I split it on that side? What do I get? I get OH.
Hydroxy group.
Mm-hmm. And then the other part would be the carbonyl with a hydrogen attached to it. Is that right?
Yeah.
Mm-hmm. If I broke it on that side. So the OH is 17. The other side would have to be 29. So here's the question. Is there any way that anything I can break apart from formic acid that's going to give me a peak at 31? Right? So is it any fragment in that molecule that weighs 15 grams per mole that I can remove and get the base peak, which is the most stable fragment and the highest abundance of the fragment present in the highest amount? Is there anything I can take off of formic acid to get a peak at 31? Or anything I can subtract from it that is 15 grams per mole?
Could you take off the oxygen that is double bonded to the?
But oxygen is 16 grams per mole though. The atomic mass is 16. If I took that off, I get a peak at 30, not 31, because the total mass is 46. Is that right?
Yeah.
Mm-hmm. So is there anything I can remove that'll give me a peak at 31 and 15 for formic acid? Because your fragments have to match the spectrum. You can't retrofitted. So it's either there or it's not. So is there anything that I can remove that'll give me a fragment that has a mass of 31 and 15?
No.
No. So that means that this spectrum can't correspond to formic acid. Are you following?
Mm-hmm.
Or it has to be for ethanol. Is that making sense?
Yes.
All right, so let's take ethanol, which is right here. I'm gonna redraw it down here. So this is so ugly. So this is ethanol. Right? So if I chop it here, let me not do that like that. No, that's a bad color, sorry. If I chop it right there, what two fragments am I going to get? All right, keep in mind, when I do that, I get a CH3, CH2, and OH fragment. Is that right? Because this is a CH2 and that's a CH3, right?
Mm-hmm.
So when I break that bond between carbon and oxygen, I'll get an OH and I'll get a CH3, CH2 fragment. Is that right? And this is 29. This is 17. Is that right? Because what I'm doing again, I'm ripping this molecule apart, breaking sigma bonds between atoms to get fragments. Is that okay?
Yeah.
All right. Where else could I cut it? I mean, I could also cut it here, right? I can cut it right there too, can I? So I can break the carbon-carbon sigma bond here. And then if I do that, then I'm left with CH3.
And then CH2 and OH.
It's 15, and then CH2OH, which happens to be 31. Are y'all following that? Is that clear or no?
Yeah. So
Yeah.
for this,
Mm-hmm.
you only basically split in half the ones that have 46. The other ones you kind of just like put them in the trash bin, like you're not worried about them anymore.
No, because we already showed that this spectrum can't correspond to these compounds.
Okay.
So the one at 60 and those with molecular weight of 60, they can't fit because this spectrum only goes to 50. And if you're doing a mass spec, it's going to pick up every mass of every compound. So if there's nothing in the mixture that has a molecular weight of 60 grams per mole, then it's not going to pick it up. And then with methanol, it had a mass of 32. So that means the spectrum should have stopped at 32 or at 33 because you're going to get an M+1 peak for every mass spectrum. So isotope peak. So if it's all the way out here to 47, then it can't correspond to that either. Does that answer your question?
Mm-hmm. I was just making sure I'm on the right track.
Yeah, you're on the right track. So we only care about the compounds that the spectrum could correspond to, right? So that's how mass spec works. You break the molecule into fragments, and then each fragment has a mass, and each mass is going to get picked up by the mass detector. All right. What about the peak at 46? I'm sorry, 47. What is that peak? If the mass of the compound is 46, what's the peak at 47?
The M+1 peak.
Yeah, it's the M. Thank you. It's the M+1 peak. And then 45 is what? Loss of a proton, or loss of hydrogen. Are y'all following? So 31 would correspond to this fragment, the CH2OH. The 15 here, that would correspond to the CH3. 29 corresponds to this fragment. All these fragments are possible because any way you can break a fragment, a molecule is going to fragment. All right. Questions? Any questions? All right. I have to clear this off. So, but it'll be in the recording. So if you need to go back and jot it down, and I'll send this PowerPoint out too. But if you need to jot it down, that's fine. But we're gonna work through some other examples too. So let's go. Let me clear this off, and then let's go to the next slide. All right. So these are your different cleavage patterns. Like when you have different types of molecules that you're injecting into a mass spectrometer, right? Depending on the type of compound, that's going to also determine how it cleaves or how it breaks off. So if you have a branched alkane, it's going to prefer to cleave at the branch points. And then notice, remember I said earlier that one fragment will have to be the radical and one fragment will have to be the cation. And so here you'll see that the radical ends up here on this primary carbon, and then the cation ends up here on the secondary carbon. That's because it's all based on stability. Which one becomes radical, which one becomes the cation is all based on stability, right? Here, same thing. If you have like an allylic type compound, like a double bond present, it's going to cleave at the allylic site. And so that's why you have this CH3 here as a fragment, and then the allylic portion here as a fragment also, right? And again, the plus charge went here because it can be stabilized through resonance, and then the radical went here. And the radical can also be stabilized through resonance, but the thing is, the methyl cation is the most unstable cation that you can make. So the radical will prefer to be there. All right, and then you have what's called alpha cleavage, which is kind of what we just saw, right? You have a functional group like alcohol, an amine, or a carbonyl, and that functional group, you can cleave on either side of it. So that's kind of what we saw with the alcohol that we were just working with. So you cleave here and cleave here, you're going to get two sets of fragments, right? If you cleave on the left side, you're going to get this fragment. Let me draw it in. You'll get that plus a CH3, CH2 fragment, right? And if you cleave on the right side, you're going to get, hold up, sorry. That's the right side cleavage. So CH3, CH2, and then the alcohol part here. And one of these is going to be the cation. I'm just going to make that this one. And one of these will be the radical. And if you cleave on the left side, you'll get a I'm going to put or. You'll get a 3-carbon chain with a primary carbon. So we're going to make that the radical plus this. And we'll make that the cation. Are y'all following that? So I'm actually breaking this carbon-carbon bond right here. Or on the other side, I'm breaking this carbon-carbon bond. All right, so if I did that to the amine or the ketone, I should get similar fragments, yes? Just with a different functional group. So would somebody draw this one? What fragments you would get if you cleaved it on the left and on the right? No takers. So I would get this fragment. I'm cleaving on the right side first. And then be the same thing plus, I'll write it out, CH2, CH3. And I'll put the radical here, right? Or I'll get this plus that, right? And I'll put the plus charge here and the radical here. Yeah. Are we following or no?
Yes.
All right. And it'll be the same thing for that ketone that's shown on the bottom. All right. Okay. Let me clear this off. And then one other fragmentation pattern that we'll talk about is here, right? So dehydration. If you have an alcohol, it'll dehydrate, and then you'll get, you should see a peak in the mass spectrum for water, which is 18 grams per mole. All right. So let's look at an example. So here we did, if we do an allylic bromination, we can see that we're going to get, this product has molecular weight of 190 grams per mole. And if we look at if we take the mass spectrum, right, we can cleave it at this branch point and we get these two fragments, right? Well, one is 148 and one is 42. And if we cleave it at the allylic site, then we should get two fragments. One is 111 and then one is 79. Right? There are other cleavage patterns that can happen, obviously, but these are the two most prominent ones that you're going to observe. All right. Is that okay?
Yeah.
All right. So now let's look at this example. We're going to say, so a patient mysteriously dies. It's believed that the patient has been poisoned by his wife. Crime scene investigators suspect that the patient has been exposed to dioxin, which is the second deadliest poison on Earth, with a lethal dose of 5 milligrams per kilogram of body weight. How would they find out? Right, the deadliest poison on Earth is what? Anybody?
Mm-hmm.
It's something that people actually use to try and look younger.
Botox.
Botox. That's the deadliest poison on Earth. And people get injections because, and it's very, very low concentration, but they get these injections that cause an inflammatory response. And so because of that inflammatory response, that's when you see, that's why you see wrinkles start kind of filling in, because it's actually a inflammatory response happening due to the injection of the Botox. All right, so the way you can find this out, if you have you can take a urine sample, obviously, but if the patient is dead, you can take a blood sample and test that blood sample for the presence of dioxin. So this is what dioxin looks like, and it has a molecular weight of 324. Got about 210 chemicals in this family, and the most toxic is the one that's shown above, tetrachlorodibenzo P-dioxin. All right, and this is also the major component in Agent Orange. And if you know anybody who was in the Vietnam War, it's possible that they were exposed. I have a cousin right now that was exposed to Agent Orange in the Vietnam War, and he's had leukemia for like 17. He's been dealing with that for like 17 years. So let's look at so the question is, if they take a blood sample, what peak are they looking for in the mass spectrum to determine if his wife is going to jail?
324.
324. If that's in the mass spectrum, then yes, she's getting locked up, right? And so we look at the mass spectrum. This is the mass spectrum after the blood sample. Is she going to jail or not?
No.
She's not.
Yeah, she is. It's
If
324 right there.
No, the base peak is 289.
that's the base peak, but the parent peak is what we care about.
Oh.
If that parent peak shows up, that's conclusive evidence that a compound with a molecular weight of 324 grams per mole is present. Are you following that?
Okay.
So we have conclusive evidence, right, that the dioxin is present because the parent peak is 324. The base peak is a fragment, right? So let's look at what could cause that base peak. Let me clear this off right quick. So the parent is 324. The base peak 289 is just this fragment, loss of one chlorine. All right, and then all of these other fragments correspond to the other peaks that are shown in that spectrum. Right, one peak that's not detected is what we call the M+2 peak, which is usually shows up when you have halogens. You get a M+2. So what's not detected also here is 326, but that doesn't mean that the parent is not present. It just means that it's below the detection limit for the instrument. All right. Any questions about that? All right. So we're going to stop here, and I'm going to give you the rest of your Friday to yourself. So only 15 minutes, but hopefully you got the email, the announcement. There's a little quiz that you can test out your lockdown browser in. There's also the instructions on how to download the lockdown browser in the last announcement. So download the browser first, then go to Blackboard and go to the testing exam, quizzes, testing exams, and open that, and you can get to that quiz. All right. And then once you take it, it's unlimited attempts. So just keep, if you hit a glitch or something like that, just keep fooling around with it before you take the test.